Hello students. In continuation with our series on assertion and reasoning, today we'll take electromagnetic induction. In our previous discussion, we have taken first discussion on how to tackle assertion and reasoning questions. What are the common mistakes made by the students? And what is the best way to attempt assertion and reasoning questions? After that, we have taken the different chapters. We have taken electrostatics. After that, we have taken current electricity, then the magnetic effect of current and magnetism. And today, we are going to discuss questions on electromagnetic induction. Let's continue our discussion on questions on assertion and reasoning on electromagnetic induction. Now, again, let's see what are the options given there. First option is assertion and reason both true, and reason is the correct explanation of assertion. Second one is assertion and reason both true, but reason is not correct explanation of assertion. Third one is assertion is true, reason is false. And the fourth one is assertion and reason both false. So now let's see the question. Assertion is only a change in magnetic flux will maintain an induced current in the coil. Reason is the presence of constant magnetic field through a coil maintains an induced current in the coil of the circuit. So here assertion, if you take only a change of magnetic flux will maintain an induced current in the coil, this is true, because if there is a change of the magnetic flux, then only there will be induced EMF developed or induced current developed in the circuit. And the reason is the presence of the constant magnetic field through a coil maintains an induced current in the coil. It is the presence of constant magnetic field. If the magnetic field is constant, in that case the magnetic flux will not change. If we assume that the area is not changing, or the coil is also not changing its area or its position, a false statement. So here assertion is true, reason is false, so that means it is the third option which is correct. Let's take the next question. An EMF can be induced by moving a conductor in a magnetic field. This is true. If you have a conductor and you are moving the conductor in a magnetic field, in that case we have seen that the EMF will be developed, which is your BLV sine theta. So you have a conductor moving in the magnetic field, so there will be EMF developed. And EMF can be induced by changing the magnetic field. Definitely this is also true. EMF can be induced if there is a change of the magnetic flux. And magnetic flux is there involving the term of magnetic field. So if magnetic field is changing, magnetic flux will change, and hence there will be EMF induced. So here assertion is true, reason is also true. Now let's just see that whether the first option is correct or the second one. And EMF can be induced by moving a coil in a magnetic field, because an EMF can be induced by changing the magnetic field. Now this is not explaining why the EMF can be induced there by moving a magnet in a magnetic field. So assertion is true, reason is true, but reason is not the correct explanation. So the second one is the correct option. Let's take next question. When a number of turns of a coil is doubled, coefficient of self-inductance of a coil becomes double. And reason is given. This is because self-inductance L is directly proportional to N. N is the number of turns there, suppose. So here, if you consider for a particular coil, because you are taking self-inductance, magnetic field linked with that one is given as your mu naught Ni by 2R if I take it at the center there. So for that magnetic flux, this will be equals to BA. That means it is your mu naught Ni by 2R into pi r square. This is magnetic flux linked with one turn. And if you want the total magnetic flux, it will be multiplied by n, because n is the number of turns there. So in that case, you can see there will be a term that is your mu naught n square pi r I divided by 2. And since you know that phi is equals to Li, so that means L will be proportional to n square. So that means this statement, when we say that the number of turns is double, then self-inductance becomes double, this is false. And second part is given that this is because self-inductance L is directly proportional to n, so this is also false. So here assertion and reason both are false, so fourth one is the correct option. Let's take next question. Assertion is an EMF is induced in a closed loop where magnetic flux is varied. The induced field E is not a conservative field. Now this is true, because the induced field is not a conservative one in this particular case. If you take that EMF which is induced there or developed there whenever magnetic flux is changing, the line integral E dot dl over a closed loop is non-zero. Now since E is non-conservative, that is why the line integral over the closed loop will be non-zero. Because if you consider that it is a conservative one, then it will be 0. For any conservative field, if you take its line integral over the closed loop, in that case it will be 0 there. So since it is your non-conservative, in that case it is non-zero. This is also true. Now let's just see the two statements together. And EMF is induced in a closed loop where magnetic flux is varied. The induced field E is not a conservative field because the line integral E dot dl over a closed path is non-zero. So this is explaining it correctly there. And so the first one is the correct option. Let's take the next question. Assertion is acceleration of a vertically falling magnet through a horizontal metallic ring is less than G. And reason is current induced in the ring opposes the fall of the magnet. Suppose if I take that you have a horizontal ring kept there and a magnet is being dropped. This is suppose the magnet which is being dropped. This is its north pole, this is south pole, it is falling. If it is falling there, in that case magnetic flux linked with this ring, metallic ring, will change. And if it is changing there, in that case there will be induced current developed in it. And the direction of the induced current will be such to oppose the cause which is producing it. And what is the cause of that change of the magnetic flux? It is the motion of the magnet towards it. So in that case it will try to oppose its motion. And as its motion will be opposed, definitely the acceleration of the magnet will be less than acceleration due to gravity. So this is true. The reason which is there, the current induced in the ring opposes the fall of the magnet. So this is also true. Because due to the current which is developed there in the ring, the magnet's motion is opposed. So again, if you take the two statements together, acceleration of a vertically falling magnet through a horizontal metallic ring is less than 0 because the current induced in the ring opposes the fall of the magnet. So this is explaining it correctly. So that means the first one is the correct option. Now let's take assertion part. If we use a battery across the primary of a step-up transformer, the voltage is also obtained across secondary. We are using a battery. That means it is the DC source. And if it is the DC source, definitely the magnetic flux linked with that will not change. Current is not changing there. So in that case, there will be no voltage across the secondary. So this is false. And the second one, if you take battery, gives a time varying current. So there is no change in the magnetic flux through the secondary of the transformer, and hence EMF is induced. If you are taking a battery, in that case it is not giving a time varying current there because it is a DC one. This gives a DC output there. So in that case this will also be false. So here assertion is false, reason is false. So that means the fourth one is the correct option. Let's take next question. Assertion is, so only a change in magnetic flux will induce a current in the coil. That means this is true. Whenever there is a change of the magnetic flux, then only there will be induced current developed in the circuit. And the reason is given, the presence of the large magnetic flux through a coil maintains a current in the coil if the circuit is continuous. Now, presence of large magnetic flux, this is not true. The presence of the magnetic flux through the coil is not essential. Rather, it is the change of the magnetic flux which is required for producing induced current there. So that means this is false. So assertion is true, reason is false. That means the third one is the correct option. Let's take the next one. The resistance of a coil for direct current is 5 ohm. An alternating current is sent through it. The resistance will remain same. Now here, if you consider that resistance is 5 ohm for the direct current, that means the R value is 5 ohm. And alternating current is sent through it. When you are sending alternating current, then it will have some impedance. And that is given as your square root of RS square plus X square. Because the coil will have some reactance there. And due to that, there will be a change of the impedance. But the statement is that the resistance will remain same. This is true. Impedance will change, not the resistance. So this is true. And resistance of the coil does not depend upon the nature of the current. So this is also true. The resistance of the coil is not depending upon the current which is passing through. It will depend upon the nature of the material which is being used, then the physical conditions or the physical factors like the length, area of cross section and other. So it will depend upon that, and also on the temperature. So now both are true. Let's now just see the two statements together. The resistance of a coil for direct current is 5 ohm. And alternating current is sent through it, the resistance will remain same, because the resistance of a coil does not depend upon the nature of the current. So here, this one is explaining it correctly. So the first one will be the correct option. Let's take the next one. Acceleration of a magnet falling through a long solenoid decreases. The reason is, the induced current produced in a circuit always flow in such direction so as to oppose the cause producing it. So you have suppose a solenoid and you are dropping a magnet through its axis. As you are dropping a magnet through its axis, in that case definitely the acceleration of the magnet will change, because it will decrease its magnet. It was just a case like you have a ring and you are making a magnet fall through its axis. In that case, there is the induced current developed, so it will oppose the cause. So this is true. And the reason which is there, the induced current produced in the circuit always flow in such direction so as to oppose the cause producing it. This is also true, because this is your Lenz's law there. And if you just see the two statements together, acceleration of a magnet falling through a long solenoid decreases because the induced current produced in the circuit always flow in such direction as to oppose the cause producing it. So this is making a correct explanation for the assertion part. So that means here the first one is the correct option. Let's take the last one. An induced current is developed in a conductor if it moves in a direction parallel to the magnetic field. And reason is, whenever there is a relative motion between the coil and magnet, the induced current is produced in the loop. Now here you have a rod and it is supposed being moved in a magnetic field. So E is your BLV sine theta. It is moving in the direction of parallel to the magnetic field. So that means theta value is 0. So in that case, the EMF will be 0. So this is your false statement. So assertion is false. Now reason, if you take, whenever there is a relative motion between the coil and the magnet, induced current is produced in the loop. Now, whenever there is a relative motion, this is true if you are taking the motion there, suppose for the coil and the magnet, then there will be induced current developed if there is a change of the magnetic flux. But in case, suppose the two, like you have suppose a coil, it is suppose being moved in this direction, you have a magnet, it is being moved in this perpendicular direction. So in this particular case, there will be no induced current developed, because here, if you consider, although there is a relative motion, but there will be no change or net change of the magnetic flux, so definitely no EMF will be induced there. So this is also false. So here assertion and reason both are false. So the fourth one will be the correct option. So these were some of the questions on electromagnetic induction. In our next discussion, we'll take up questions on alternating current.